we already see that when the meta center is above the center of gravity, then we can say that the floating bodies or the partially submerged bodies will be in the stable equilibrium, and if meta center is below the center of gravity, then it is in your unstable equilibrium. So if I can say, let us suppose this is the line, I am saying, let us say this is the point M, that is meta center. Here it is your center of gravity, and here it is your center of buoyancy. Right? This is for stable equilibrium. This is for stable equilibrium, and for unstable equilibrium, the center of gravity is in between the meta center and center of buoyancy. This is unstable equilibrium. Unstable equilibrium. From this we can say that this GM is known as metacentric height. This GM is known as metacentric height, and from this figure you can write that this BM, the distance between BM will be equal to BG plus GM. BG is the distance between center of gravity and center of buoyancy. GM is your metacentric height. So from here you can write this GM will be equal to BM minus BG. This GM will be equal to BM minus BG. In this formula, if this GM is positive, then we can say it is a stable equilibrium. If this GM is negative, that means from here we can say it is unstable equilibrium. And if G and M coincide, that means GM is 0, then we can say it is neutral equilibrium. It is neutral equilibrium. And this BM is known as metacentric radius. This BM is known as metacentric radius, and metacentric radius can be calculated with the help of formula. Metacentric radius will be equal to least moment of inertia upon volume of fluid displaced. Volume of fluid displaced. Right, this is the formula for metacentric radius, that is the least moment of inertia divided by volume of the fluid displaced. And let us see what is this least moment inertia. What is this least moment of inertia? I is the least moment of inertia, or we can say this is the moment of inertia of that surface of the body which is intersected by the free surface. This is most important, that the least moment of inertia is the moment of inertia of that surface of the body which is intersected by fluid, or you can say which is intersected by the free surface. Suppose I can say, let us find what is this. Let us say this is the free surface. In this you placed a body, a conical body you placed in it. Let us say this is the conical body here, which is submerged in this fluid. This is the conical body. The surface of this conical body, this surface this surface of this conical body is intersected by this free surface. So we have to take the moment of inertia of this surface, and I can say that if you cut this from like this, you have a surface, this is the surface. This surface has two moment of inertia, one is about this axis, another one is about this axis. If we talk about, this is the body, right, and let us say this is the free surface, right, this is the surface which cut this surface, free surface cuts this body at this point. So we have to take the moment of inertia of this surface, and this surface which comes, this surface will have two moment of inertia, two axes are there, right. So out of this you have to take the least moment of inertia, right. A surface has two moment of inertia. If I cut this, it has two moment of inertia. One is about this axis, let us say this is y axis, and one is about this x axis. So you have to take the least moment of inertia in this calculation of your metacentric radius. And just most important thing is, it is the moment of inertia of that surface which is intersected by the free surface, right, which is intersected by the free surface. That surface which cut, this free surface is cut that surface moment of inertia you have to take, and out of those two moment of inertia, the least one you have to take, right. Also I can say that for stability, if you want that the body which is submerged in the fluid is stable, then we can say that metacentric height is very large. We prefer that metacentric height will be large. If the metacentric height is large, if this GM is large, right, then in that case we will say that in that case the body will be more stable. If you think about the ship, let us say this is a ship. This question will ask in the, maybe in the interview, or you can say in the objective of engineering services. Let us say this is a ship, right. So this rotation of the ship, this rotation about this axis, this rotation of the ship is known as your rolling. This rotation is known as rolling, and this rotation of this ship is known as pitching. This rotation is known as pitching. And if you can see that the moment of inertia of this rolling moment of inertia is less than the moment of inertia of this pitching, right. This is more, the moment of inertia along this axis is more than the moment of inertia about this axis. So if you talk about the ship, then in the ship we can say that moment of inertia of rolling is least. So if you want to design the ship, then we will design based on rolling. So design of ship, that whether the ship will be stable or unstable, that is design of ship will be based on the, while considering rolling motion, because the rolling moment of inertia is least than the your pitching moment of inertia. One more concept, one more term we have in the metacenter. The last term is the time period of oscillation. Time period of oscillation, right. We can say that if you give that this submerged body will be having oscillating, that this submerged body, partially submerged body will be oscillating, right, and that can be imagined and that can be assumed that they are oscillating around metacenter as the axis, as the center, metacenter as the center, that body is oscillating. So we want to find what is the time period of that oscillation. So the time period of oscillation will be equal to, I am just writing the formula, 2 pi under root k square upon gm metacentric height into g. 2 pi under root k square upon gm into g. Gm you can calculate by this formula. G you know, k is known as radius of gyration. K is known as radius of gyration, and you will easily calculate this radius of gyration. How you will calculate? You know that least moment of inertia will be equal to your area into k square. Area into k square. So from here you will easily get this value of k. Area you know, I you know, then you will get the k. So if you see from here, if you see from this formula, most important concept is, if gm is very high, if gm is high, if this gm is large, then this time period will be less. If gm is more, then the time period of oscillation is less. Time period is less. Time period is less means that this body will oscillate very fast, like this, right? Time period more means it will take more time to complete one cycle, like this it will go, and time period is very less, that means very less time it will take to complete the oscillation. So the time period is less if the metacentric height is more. So if we can say that if the metacentric height is more, then the ship or then the body will be more stable. But disadvantage is with the large metacentric height, the disadvantage is that body time period will be very less, right? If time period is less, then it will go under frequent oscillations, very fast oscillations. If the time period is less, then we can say the body is uncomfortable. The body is, or the ship, if we talk about ship, the ship will be very uncomfortable. So we have that we cannot make this metacentric height very large. If you think about stability, then you have to take this metacentric height very large, but as you take the metacentric height very large, the time period will be very small. So you have two types of ship. One is the passenger ship, in which you will carrying the passenger, and another one are warships, which are used in the wars, like your INS and so on. In the passenger ship, our most priority is comfort. We want that passenger will feel comfort when they are traveling through the ship. But in the warship, our most favorite priority is the stability. During the war, we won't allow the ship that ship is unstable. We want stability. So in the warship, the metacentric height is more than the passenger ship, and generally in the passenger ship, the metacentric height will be around 0.5 to 1. Metacentric height will be around 0.5 to 1, and in the warship the metacentric height will be around 1 to 1.8. It will be around 1 to 1.8, because in warships we want more stability. So if you want more stability, then the metacentric height will be more. If you want more comfort, then the metacentric height will be less. So this is all about your buoyancy chapter, that what is the buoyancy force, principle of flotation, and equilibrium of the completely submerged bodies and equilibrium of the floating bodies or the partially submerged bodies.